Excellent. Perfect. Thanks a lot, everyone, for joining, and thanks a lot for having me here. My name is Alex. I'm faculty at the University of Illinois Urbana-Champaign in the ECE department, working broadly on computer vision and machine learning topics. And before I get started, I do want to thank all the amazing collaborators that I had the pleasure of working with. All the results that I'm about to show are due to their work. Now, I'm sure it doesn't come as a surprise to anyone here when I'm saying that a lot of computer vision tasks have seen quite a bit of success in the last decade. Tasks like object detection and retrieval, scene understanding, and object segmentation have witnessed a remarkable progress. So, for instance, for semantic segmentation, a task for which you see results at the bottom of the slide, we were able to achieve remarkable results in quite complicated scenes. Similarly, if you're talking about videos and we do want to detect and track objects, we can do so even if we move those objects out of the frame, as you can see on the right-hand side. Not only can we briefly move these objects outside the video for a short amount of time, we can bring them back one at a time, or shuffle them around, or even hide them below the tower, and then play around with a scissor for about a minute. And I'll just do a fast forward here if I can, because I don't want you to wait for a minute until something happens. And then we'll shuffle I guess, the cans around for a bit more, such that even I don't know anymore where which can went. And once we lift the tower, methods are able to figure out which can went where and what's going on. Now, we can obviously use these remarkable achievements to build new apps based on that. So, for instance, let's try to build an app, and I do have to say I use some videos from Gemini 2.0 here, just to illustrate my main point. I'd imagine you're getting a video like the one that you're seeing here, and you want to figure out, where are the lions walking, and what are they doing across a range of scenes. And if you want to do this, there's essentially two ways you could go about doing that. One is, we could train object detectors, we could train action detectors, and we could essentially take many of the tools that I initially talked about and put them together to achieve this. Or maybe the other approach to doing that is to build what I call for now an anything machine, where these types of capabilities essentially emerge automatically. Now, just to give another example, imagine you're at this scene here, you're recording a video with some handwritten notes and a few bowls shown in the video, and you want to figure out, what did you record? What are the types of objects, the items, and what was their price? And again, we could do exactly the same thing as I said before. We could train, for instance, an OCR system. We could train a text characterization system and essentially handcraft such an app, very specialized for the particular task that we care about. Or alternative, we build an anything machine where these types of capabilities emerge. Now, what are these anything machines that I'm referring to? Well, I'm sure it's anyone's guess here, right? These are the foundation models that many of us are probably working with these days. Essentially, they're deep nets, very large deep nets, trained on really large, often unlabeled data sets, and they are able to handle a variety of tasks in essentially a zero-shot manner, where, as I said before, a lot of capabilities emerge without us having explicitly trained these models to have these capabilities. Now, just to give a few examples of these types of foundation models that you might have heard of, CLIP, SAM, Dino, classic large language models, but also text-to-image or text-to-video generation models are now among the category of foundation models. Now, just to make it really clear, what do I mean by capabilities emerging? For instance, if we look at CLIP as an example, I'm sure everyone here has seen a picture like the one on the left-hand side, which essentially shows how CLIP works. You take as input an image, you feed it into an image encoder, and then you get an image representation and you compare that image representation to a set of text representations. The text representations are computed via a text encoder that is fed with prompts like, is this a photo of a plane, a photo of a car, a photo of a dog? And we essentially then compare the text representation to the image representation and retrieve the highest scoring one, and that's going to be our class label. Now, when we train models in this form, we can obviously use it on any data set that you will, and this is exactly what the researchers did, and they compared it, in, in this plot on the right-hand side on 20-something data sets, and what they observed is that despite the fact that the model was never really trained on these types of data set, it actually had remarkable performance improvements compared to even train models that are trained upon a ResNet 50 based feature extractor on the images. So that's essentially what I mean by capabilities emerging, despite the fact that the models were never really trained to originally have these capabilities. Now, in this particular talk, I want to now show how we can use these types of foundation models for specific tasks in computer vision, tailored towards, I guess, the agriculture domain. And I'll try to focus, if time permits, on 3 different tasks. One is more object detection, tracking, and retrieval, and that refers to a CVPR 2025 and actually also a NeurIPS 2025 paper that's, I guess, about to be released. You can already find it on arXiv if you want. I also briefly talk about some recent work that we did in the scene understanding domain, introducing a spatio-temporal large language model to address challenges in classic large language models related to concurrently reasoning about both the space, the 3D space, as well as the time domain. And lastly, I'll talk a bit about work on object segmentation that I did together with students and collaborators, where we're interested in tracking essentially anything within a video, only specified by a text prompt. And that was prior work that we did about 2 years ago. All right, let me dive right in. First work is titled RELOCATE. As I said before, it's with an amazing set of collaborators, and it's a CVPR 2025, and there's a follow-up at NeurIPS about to be published, I guess, in 2 months from now. This work focuses on visual query localization. The task of visual query localization is to essentially find when and where an object appears in a long video. And for this, we want to use a reference image of the object. So if you look at the images at the bottom of your screen, you can see on the left-hand side, there is some tape, for instance, and then we're given a long video and we want to figure out in which frame does this tape appear, and particularly in which frame does this tape appear last. Now, these types of tasks are very challenging. As you can see, the query image is often very low resolution. It's very noisy. And on top of that, the scenes in the videos could be very cluttered. The object could be a very small object in those scenes. And even as a human, I myself sometimes actually have challenges finding the object. To demonstrate this, let's look at this example. Here's the query object. And then we're given a video like the one that you see on the screen here. And the object is barely visible. It's highlighted at the bottom left of this video. And it never really comes into full view either. That's what we're essentially dealing with. Here's another example. We are interested in this pen, presumably a pen. And here is the type of video that you see as input. The pen moves very quickly across the frames, and it's quite confusing. Here's another example, yet another pen. And if I look at this image, I would at first have a hard time figuring out where exactly is the pen. And there is then another example here. I don't even know what type of object that is. Probably another pen or a knife of sorts. Anyway, I think you get the idea. Query object, very low resolution. The video is sometimes very blurry, very noisy, shaky camera. that's the type of task that we're dealing with. And here is the example from what I showed before as well. Now, how has prior work addressed this type of task? Usually they pursue some sort of uh, three-stage approach based on detection and tracking. Perform some sort of frame level detection, identify the most recent detection, and then do some bi-directional tracking, both forward and backward, to figure out where's the last frame. There have been quite a few refinements of this approach using negative frame sampling for training, leveraging background objects as context. These are a few examples, and you can find more in the corresponding papers. Now, we wondered, how can we use this emergence of foundation models to address this particular task? And that's exactly what we did in this RELOCATE paper. And I should emphasize that the resulting approach is entirely training free. We did not train anything. All we did essentially use publicly available foundation models, put them together in some reasonably straightforward way, I would say, and at the end of the day, achieve state-of-the-art results. And I'm emphasizing this because I do want to encourage people to think about how can you use these types of models for the tasks that you care about. I think there's a lot of benefits to using these types of models, and we have not quite leveraged these benefits just yet. So what did we do exactly? There's a couple of stages that we go through. First stage, we called it kind of the prepare stage. We essentially extract features, SAM to segment the object, and then Dino features from the corresponding video frames. And then first thing one can do is you simply compute some sort of cosine similarity between the query object, which you can see here at the bottom of in middle bottom of the screen, for which we also extract the masks and the features. And we compare the resulting features with, I guess, all the frames, and we try to identify where does the object appear last. We perform some sort of non-maximum suppression as well. Afterwards, we go to the refinement stage, which is essentially just cropping the corresponding frame, meaning we kind of zoom in, if you will, and do the same thing again. We refine the tokens and recompute the similarity score and filter, just to get kind of a close-up view, if you will. Afterwards, very similar to the baseline approaches, we perform some tracking to bidirectionally track the last candidate using essentially SAM2, just to identify, is the object appearing close by as well, and we just haven't found it yet. Now, the last step is we kind of reiterate, meaning we add whatever objects we found as additional queries. So we expand the query pool, and we then repeat this search, refine, and track procedure, essentially by having hopefully more information about the object that we care about. And because we have more information, we can find the object in particularly challenging scenarios, say if it's about to go off screen, for instance. And that's where refine actually is particularly useful. Now, this is the overall pipeline. As I said, it looks maybe somewhat intimidating at first, but at the end of the day, it's really just extracting features, cosine similarity, a bit of cropping, tracking, and repeat. So nothing too fancy overall, I would say. And what we were very surprised about is, as I said, there was no training whatsoever. We only extracted these features, put them together, and we applied this method on the Ego 4D Visual Query 2D challenge. And we ended up at the top of the leaderboard, again, without any task-specific training whatsoever. Not only did we end up on the top of the leaderboard, but we actually significantly improved results compared to prior works that did spend quite a bit of time on training on the particular data sets. So what you can see in the table that I'm showing here on the slide is a couple of columns. STAP is essentially, think of it as spatio-temporal average precision. TAP is just looking at time, so it's temporal average precision. And then there's some sort of success and recovery metrics. The different rows are different prior works. RELOCATE, as I mentioned before, is the work that we designed. And on both the validation set as well as the test set, I would say we improved upon prior work by quite a margin, which was very exciting to see. And I think is particularly useful in something like an agriculture context. Now, there's a couple of limitations that I would want to point out here. One, we did have to prepare the videos for search by extracting the corresponding features, and that can be particularly time consuming. Essentially, because we have to pool dino features with SAM masks for all the objects within a scene, and that just takes a lot of time. Now, if you have kind of a database of videos, and you can do that ahead of time, then that is feasible. But if you want to do a search kind of on the fly, then doing this pre-computation is maybe not feasible. And this is exactly where our follow-up work on the region encoder network comes in. And as I said before, this is about to appear at NeurIPS 2025, early December this year. Now, what we did here is essentially to pool dino features with SAM masks, but then train a network to kind of do that automatically. And that gives us what we call these region representations without ever having to eventually extract a segmentation mask. So while we have to do that at training, we don't have to do that anymore, I guess, at test time. And instead, we end up having a network that can then do this automatically, and it can be prompted by essentially just points. And you can see that in the left-hand side on the input image. There is a couple of additional points. Literally think of them as clicks, locations that you specified. They go through some embedding network. We get the corresponding point prompts, and then we just cross-attend to a classic image encoder, and we train the resulting network to obtain what we call these REN tokens, or the the aligned REN tokens. And aligned because they're essentially aligned with some feature similarity loss to, say, some dino features. There's two losses, as I said before. There's the contrastive loss, where we generate two augmented views of each image, and we then extract tokens from both views using the network that I just described before. And there's not the REN tokens corresponding to prompt points within the same region are then essentially treated as positives, and everything else is treated as negatives. That's the one loss for training this. The second loss is the feature similarity loss, which essentially prevents drift from the original feature space. So we essentially want to make sure that the resulting features still carry a lot of the semantic and perceptual information that the original features carried with them. Now, when would you want to use these two types of tokens that our model provides? Essentially, what we found was that tasks that involve further learning, you might want to use the REN tokens, but for zero-shot tasks where you essentially want to benefit from them, the REN tokens are better for discriminative tasks, but the aligned REN tokens are better for tasks that leverage image encoder properties. And that's kind of intuitive because the REN tokens are specifically designed to maintain the alignment, essentially. So with that said, let me show you a couple of results again on this visual query localization task in 2D. And we were able to further improve the results. Again, same table as before. Now RELOCATE is one of the baselines. REN is, I guess, our latest approach. And if we just look at the column of spatio-temporal average precision, for instance, we can see that we were able to improve from 0.35 to 0.40 the spatio-temporal average precision, which is the most challenging metric because it essentially assesses whether you get the object right, both in terms of in space, meaning on the image location, but also in terms of time. And we were also able to show, compared to prior works, that the REN approach is actually quite efficient in terms of GPU memory. And you can see that on the right-hand side, where the x-axis is the point prompts per batch, and the y-axis is the GPU memory that we used. So summarizing that first third of my presentation, regional representations, I think, are particularly powerful these days. And particularly if you're interested in efficient visual query localization, I think there's an interesting solution that you might want to think about. Now, with that, I want to switch gears a bit to the second third and talk a little bit about our work on spatio-temporal large language models, which we subtitled as Reasoning about Environments and Actions. And the idea behind this work is, or the motivation behind this work is that we envision agents to operate in real-world environments. Imagine you have an agent operating in your home, and it kind of has a decent understanding of your home. It has been there before. It should consider not only what it currently sees, but the home as a whole, which is, I guess, very similar to what we as humans would do as well. If you have lived in a place for a while, you know your place kind of inside out. Um, and so we want these agents to be able to leverage a global scene representation. In addition, obviously, you have very localized both spatial and temporal context in the form of, let's say, a video, right? As humans, we have our eyes, we see where we currently are and what we're currently doing, but that's very localized compared to the overall environment. And so we're envisioning agents operating in this type of scenario, and then we want them to perform tasks like action planning, affordance prediction, finding items that we placed somewhere in the past, estimating relative distances, but also estimating relative directions. And what we found is that if you ask classic large language models to address these types of tasks, they struggle quite a bit with it, which is intuitive because they are often mostly text-based, and how to exactly take into account a global scene representation as well as a local observation is maybe non-trivial. There has been a bit of prior work, primarily obviously using multimodal large language models themselves, but then also expanding them by using video data or 3D data. For the latter ones, videos are often treated as a set of multi-view images as opposed to containing both spatial and temporal information. And oftentimes, many of these works actually require additional information, for instance, in the form of depth maps per frame, which we did not want to take into account. So first thing we did then was essentially collect a data set that enables us to reason about, on the one hand, events unfolding in an egocentric view, but at the same time understand from an allocentric view how are these events anchored in a global environment. And as I said before, I believe that this type of reasoning is particularly important for embodied AI tasks, for situational awareness tasks, but also for spatio-temporal question answering. So contributions of this particular work are then a data collection pipeline that allow us to collect the corresponding data to train a set of spatio-temporal large language models. And the data set contains 5 different tasks, as I mentioned before as well. One of them is relative direction. It essentially asks how a person's body direction changes with respect to an object across 2 actions that the person performs. So imagine you're standing at the sink first, and then you're turning towards the oven, and the data set might ask, how did the location of the fridge change with respect to your pose during those 2 actions? I believe I have an example here. In this case, is the microwave to the left of the person when the person is performing put down the knife, and also to the left of the person when performing, pick up the plate. And the ground truth answer would be the microwave remains to the left of the person during both put down knives and pick up plate, because in this example, the person didn't really rotate. Relative distance is a very similar task, but assesses the person's proximity to one or more object changes over time. And there is another example here, does the person move closer to the hob between turn off rice cooker and serve curry? And I also show the ground truth here, which in the interest of time I not go through. Yet another task is find my item. So we are interested in localizing objects based on visual evidence and infer navigation steps towards these objects. and the objects may not be visible within the current observation, but might only be visible in the global 3D scene representation. And there's an example, where's the tarragon and how can the person get to it? Yet another task I mentioned before, furniture affordance prediction. Goal is to predict the furniture the person will interact with next. An example is which of the following objects does the person interact with next given their previous actions and current motion. So you essentially have to observe what did the person do beforehand and what is it about to do next within the scene, where is it moving towards? And last one is action planning. Anticipate the next plausible action at task and provide the corresponding navigation. For instance, again, on the right-hand side, you can see some example. And the question would be, we are performing a cooking assembly task with the following sequence of actions: put down tray, put down sponge, take glass, wash knife. Based on the video, what should I do next? And how can I get to the place where the next step takes place? So these are the types of tasks that we're interested in. Now, it's very hard to, I guess, find any data sets that would allow you to train models for this type of task. So first thing we did was we developed the dataset collection pipeline, which benefits from amazing work that other people have done on collecting data. We just leverage this work and combine it in, as we think, an interesting way to enable these types of reasoning tasks. In the interest of time, I guess I'll not go through the overall pipeline here, but mostly skip through the steps, and I leave you to find those in the paper. We then also designed two baseline models, one that essentially operates on the 3D point cloud directly, the other one which takes the point cloud but then kind of compresses it. And what we wanted to understand is how important is the 3D information, or is it sufficient, or can we actually compress the 3D information? Again, I jumped through a couple of things. Maybe I pause a bit on the results. The way we evaluated things is via an LLM judge, or actually two LLM judges. One is ChatGPT, the other one is Gemini 2.0. And what first thing we find is that if you use classic large language models, they struggle quite a bit with that task, as you can see in the, say, rightmost column, where we show the overall and average type of accuracy for two judges, C, ChatGPT, G, Gemini, and different models that are listed on the leftmost column. Now, we can obviously then fine-tune on the data set, which I just described. And first thing we observe is that there's quite a jump for the baseline models when being trained or when being fine-tuned on the particular data set. And lastly, we showed that by integrating point clouds in the way we studied, we can get some further improvements here. Now, we can also show some zero-shot results. So instead of only evaluating the model's results on the data set that we collected, how about using some external data set and verifying that the learned properties extend, and we can show that improvements hold true there as well. And in the interest of time, I skip through the details. And maybe summarizing this particular work, reasoning about environments and actions, I believe is something very exciting that will have quite a bit of impact down the road. And we do need to work quite a bit more on enabling large language models to perform spatio-temporal reasoning. Agentic tasks is another thing that's interesting. I don't know how I'm doing in terms of time, Jimmy. I just want to briefly check in. How much more time do I have? Should I skip over this part, or?
We probably can go another 5 minutes and then we'll want to get back on track.
All right, perfect. I used 5 minutes to go through this last work, which is, again, thanks to an amazing set of collaborators that I had a fortune to work with. Here, maybe let me start by going through a case study. Imagine you're given this video that you see here, and you're tasked to detect and track the piglets in that scene. How would you go about doing something of that sort? Well, first thing you would probably do is go to GitHub and look for pre-trained open source models. What you'd find is that a lot of models are commonly trained on either the YouTube VIS dataset or the OVIS dataset. Now, the YouTube VIS dataset contains quite a few objects, 40, but unfortunately no pig. The OVIS dataset, similarly, 21 objects, but again, no pig. So we're kind of out of luck. So what can we do? Well, if we cannot use a pre-trained model, how about we collect our own data? Segment the target objects, retrain the model on this new data, and essentially test and evaluate the trained model. How much time does this take? Well, you need about 3,000 annotations. Not too many, so it's doable, but not that easy either. The whole process can certainly take a few months. You probably need to find the data, annotate the data, go through a couple of iterations of training your model to make sure everything works fine. And then someone comes around and says, well, now I don't care about pigs anymore. How about these nice capybaras here? And, you're going to sigh and say, okay, well, same thing again, repeat. So essentially, point I'm trying to make here is, the whole process is expensive. It's not scalable. Can we do something better than that? And that's really what we were interested in this particular work. Essentially trying to track anything. Again, given as input a video and a text prompt specifying the object that we're interested in, can we then detect, segment, and track the object of interest? So in this example, the prompt might be, segment me the children, the toy car, and the bicycle. And we want to see an output like the one illustrated on the right-hand side, which is in fact an output of the model that we designed. And you can access the model by following the QR code on the top right of the slide. Again, similar to work before, we stand on the shoulder of giants and essentially benefit from visual foundation models, which we then link across frames. In short, imagine the input video. We use grounding dyno to get bounding boxes based on the input text prompts. Once we have the bounding boxes, we use a SAM model, which I also mentioned at the beginning of this presentation, to get the corresponding segmentation masks. We get this for every frame. Now you have a set of per image segmentations, which can actually be quite noisy. So it's non-trivial to link them. And this is where our work Deva comes in, where we essentially devise an approach to link those segmentations across time to get the result that I also showed everyone before. And if you want to apply this on this pig data set, here you go. Here's exactly the result. And we were actually quite surprised by how well this works. It's not perfect, but I think decent quality results. I would say that are quite useful. Now, nice thing is no retraining, no change of the method at all. We just provide this video as input, ask it to figure out where are the capybaras, and it does so in minutes as opposed to months. And just to add one more, if you're interested in guinea pigs and chickens, here's another example of this working pretty much out of the box. Conclusion, I would say, foundation models simplify many tasks. You should definitely think about how you can benefit from the works that have been done in the field. There's a lot of challenges that obviously remain, as I tried to allude to with the talk in the middle. There's significantly more work needed in this space. We're by no means anywhere done. And with that, I'm going to stop. Thank all my collaborators and funding agencies. Happy to answer any questions now or at any point in time. Just always feel free to reach out. Thank you.
Fantastic. So we will take one question before we toggle over to Andrew. Quick note, all of the links to the 3 papers that Alex talked about, I've linked there in the chat, as well as his landing page if you want to learn more about his research and connect with him offline. I'm going to try and kind of generalize this question. How does the spatial-temporal LLM achieve robust, generalizable, and causally coherent reasoning about dynamic physical environments from an embodied perspective, integrating spatial relationships, temporal sequences, action affordances, and multiple agent interactions without relying solely on statistical patterns or requiring explicit geometric or multimodal grounding?
Yeah, that's a great question. So I unfortunately didn't have the time to get into the details of our architecture. There's a couple of things that we put in place to try to enable this beyond just trying to, if you will, extract things purely from the data. So, for instance, when we take the observation, the short video clip, we actually line it up with the point cloud, and we're trying to detect, where in the scene was the observation taken. And we don't do that in a hard-coded way. We essentially just encode, if you will, the point cloud with corresponding positional encodings. And you might have realized that, in some of the results we had with positional encoding and without positional encoding. That was, for instance, exactly that property. So one thing we try to make sure by doing this is to essentially provide to these large language models the ability to ground themselves within the larger physical space. Obviously, other aspects, we ask it to retrieve from either the point clouds themselves, and I think that's another component different from different from many standard large language models. We try to figure out what are good ways to incorporate these point clouds, and I again only touched upon this very lightly, but we wanted to understand, can we, or to what extent can we compress these point clouds such that a 3D understanding remains? Have we successfully answered that question? I'm not entirely sure. I think that, as I also tried to mention at the end, I think a lot more work is needed in that space. But I think showing that this improves results compared to not doing anything about space and time is probably, at least according to my opinion, a first step in the right direction.